Hello, this is section 3.2 for Calc AB, and today we're going to be focusing on two important theorems, Rolle's theorem and the mean value theorem. Both are very similar, just have a slight difference in them. Now, before we jump in, just a reminder, the extreme value theorem says if f is continuous on the closed interval from a to b, and f has both a min, then f has both a min and a max on that interval. And go back in section 3.1 and review that. But as long as you're continuous on a closed interval, you are guaranteed at least one minimum and at least one maximum. Okay? And of course, endpoints. Remember to include endpoints. Now, Rolle's theorem says let f be continuous on the closed interval a to b and differentiable on the open interval. If the endpoints equal each other, then there exists at least one number c in the open interval a to b such that the derivative at c equals 0. All right, so let's look at this visual down here. So notice it meets our requirements. The function's continuous on the closed interval. Yes. Differentiable on the open. Yes. No sharp turns, no vertical inflection points or anything like that. Vertical tangent lines, remember. And the endpoints equal each other. So yeah, it meets all three requirements for Rolle's theorem. Then, and you can imagine this, if you are trying to get from point A to point B, if you go off of that horizontal line, you'll have to curve back around to get to B, even if you go below it too. So you're going to have to create at some point in that interval a slope of 0. Okay? So this theorem gives conditions that guarantee a horizontal tangent that can be found somewhere in the interval which the max or min is not an endpoint. So that's kind of in layman's terms. And that's what this did. We found a C where we had so to get from A to B, we had to curve around, and that created that slope of 0 there, where the derivative equals 0. So here are some more examples where we're continuous, differentiable, endpoints equal each other. Sure enough, we have a place where the slope is 0. And in this case, we had two places. And then here's where you cannot use Rolle's theorem. And you can see it fails that second part. It's not differentiable on the open interval. We had this sharp turn right there where the slopes are not the same from the left and the right. And sure enough, the derivative is not 0. The derivative would be undefined right there. Okay? So here's an example of if you'll have to do this on an assessment. Determine whether Rolle's theorem can be applied to this function on the interval -1 to 3. If it can, find all values of c in the interval such that the derivative equals 0. Okay, so guys, you have to first justify that you can use Rolle's theorem. So you need to tell me, is it continuous on the closed interval? And you might note, hey, there's an asymptote, potential asymptote or open circle at -2, and I agree with you, but notice -2 is not in the interval we care about. So we're okay. This is a continuous function from -1 to 3. Is it differentiable? Yes. And you know that. That's a rational function. As long as we're not talking about at -2, everything else is good to go. And then lastly, you need to confirm that the endpoints equal each other. So plug -1 and 3 into your function, and yes, you get 0. It doesn't matter what value you get as long as it's the same. It just happened to be 0 for this problem. All right, but all three conditions have been met. So somewhere in the interval from -1 to 3, Rolle's theorem guarantees there's a horizontal tangent line. There's a derivative that's 0. Slope of the tangent line is 0 somewhere within that closed interval. So if you don't find somewhere, you've done something wrong. Rolle's theorem guarantees that. So that's what we're going to do. We're going to do the derivative. So here's my low d high minus high d low over low low. And then clean it up so we can set it equal to 0. Oh, lovely. It doesn't factor. Now remember, we only care about the numerator, setting it equal to 0. So we use the quadratic formula. And we get this -2 plus or minus the square root of 5. But that's two answers. We're not going to usually keep both of them. We'll end up throwing out the -2 minus the square root of 5 because that falls outside of our interval. But the most important thing is we were able to find -2 plus the square root of 5 that falls in our interval that has a slope of 0 because we set the derivative equal to 0. There's our guaranteed answer. Isn't that cool? All right, now here's another example using Rolle's theorem. So determine whether Rolle's theorem can be applied to this sine of 2x in the interval. If it can, find all c values of c in the interval such that the derivative equals 0. C. All right, so it is continuous. We know that's a continuous function there. It's differentiable. We're good to go. We checked the endpoint. So notice I'll always look for you that you've checked these 3 requirements. This is so important to include in your work. Then from there, we found the derivative. Make sure you use your chain rule. Don't forget to multiply by 2. And then set that equal to 0. But remember, we only care within this interval. Okay? I might have to review some of your pre-calc trig concepts. It's something, if something I do on the notes does not make sense, email me or come see me. I will help you. All right, the next theorem is the mean value theorem. And a lot of times we abbreviate it with MVT, and that's perfectly fine. So the mean value theorem says if f is continuous on the closed interval from a to b and differentiable on the open. So notice it starts off the same way as Rolle's theorem. Then there exists this number c in the open interval such that the derivative at c is equal to the slope of the endpoints. So I'm going to scroll back up here. I didn't mention this earlier, but if you see it now, do you notice that the slopes are parallel? See how the slope is 0, slope is 0? That's what we're doing here. We're saying instead of making the endpoints equal to each other, we'll just say, okay, the endpoints can be anything, but we're guaranteed that these slopes are going to be parallel. They're going to be equal to each other. The lines are parallel, the slopes are equal. There we go. Okay? So it takes out that requirement that the endpoints have to equal each other. But there's, and you can visually see this, to get from A to B, if I go off that horizontal line, then yeah, I'm going to have to curve back around, therefore creating, in this case, a slope of a tangent line that's the same as the slope of the secant line. Okay, so here, yeah, I said this already. All right, this theorem guarantees the existence of a tangent line parallel to the secant line that goes through the endpoints. And it implies that there is a point C in the interval where the average rate of change, meaning the slope of your secant, equals the instantaneous rate of change, slope of your tangent. Right? So we're actually taking away, it's just like Rolle's theorem, it's just not requiring the endpoints to equal each other. Now, what's really tricky about the mean value theorem is up until now, we've always found the derivative and set it equal to 0. But in this case, we don't. So that's the one weird thing about mean value theorem. So here's an example. Apply the mean value theorem to this function on the interval from 2 to 6. Find all values of c in the interval such that the derivative equals the slope of the endpoints. So first, just like Rolle's theorem, you have to identify, you have to justify that you can use the theorem. So state that the function's continuous. I probably should have written the name. F of x is continuous to be better. That would be better to write it that way. It's continuous on the closed interval, which it is. You're good to go. As long as you're in the domain of this radical function, you're good to go. And the function is differentiable from 2 to 6. Yeah, that's all you have to say. So then from here, we're going to find the derivative. So that's what we do here. We found the derivative. Make sure you use the chain rule, although the derivative of the inside is 1. And then this is what's different. Notice I go off to the side and find the slope of the endpoints, and you get 1/2. So you're going to set the derivative equal to the slope of your endpoints 1/2. And that's where you're so used to setting the derivative equal to 0 to get those critical numbers from the last section, and even what we just did earlier, Rolle's theorem, you're setting the derivative equal to 0. But with mean value theorem, you set your derivative equal to the slope of the endpoints, and that's a little bit different. All right? But when you do that, now you can algebraically solve. So I ended up multiplying by 2, squaring both, or raising both sides to the -2, it looks like, and then solved from there. And I actually got c equals 3. And remember, if you've met the requirements, you are guaranteed an answer. So if you don't get one, you've done something wrong. Okay? Or maybe your requirements are wrong. So I'm going to move me up here so we can look at this last example. Okay, apply the mean value theorem to f of x equals this lovely function on the interval -pi to pi. Find all values of c in the interval such that the derivative equals the slope of the endpoints. Okay, so this function's continuous and differentiable. We're good. Continuous on the closed, differentiable on the open. Okay, I found the derivative. Over off to the side, I found the slope of the endpoints. Got a nice pretty 1. And now I'm going to set the derivative equal to 1 and then solve from there. So when is cosine of x equal to 0? Remember, visualize the graph. Where does that graph hit the x-axis within the interval I care about? And I actually got 2 answers on this one. There you go. And remember, these c values are where the slope of the tangent line is the same as the slope of the endpoints. Okay? So 2 very important theorems, and you have to make sure that you show me this really important justification step before you start to use the theorems. So state that the function is continuous on the closed, differentiable on the open. For Rolle's theorem, it has 1 extra step, and that is you have to show me that the endpoints are the same, making the slope of the endpoints 0. So you can just simply set your derivative equal to 0. So definitely do your homework and practice these theorems and make sure you're doing the justification part before you use the theorem, okay? And please email me if you have any questions.